Hey Quinn, how's it going?
Good, how are you?
You know, technology is getting me down. My computer died on me in the middle of my last class. It died with like 64% battery power because my computer issued to me by the school is ancient. Um, so I'm now plugged into power, so everything should be fine for you guys. But I'm bopping along, running through an R script, and just totally dies on me. But that's the way it goes. Kelsey, talk to me. Kelsey, are you there? Where is Kelsey?
Sorry, my audio has been really bad the past day.
Okay. You didn't tell us that you were a finalist for the faculty award.
I didn't know that I needed to.
Oh, I used to be chair of that committee for about 5 years, and it was like the funnest committee to serve on of all the committees that I've served on while at Williamsville College. And it was because I get really tunnel visioned about our own department here in biology. I think we have a great major. I think we have awesome students. I think we do a really good job of preparing you guys for whatever you do next. And so I tend to think, woo, biology is so awesome. And then when I served on the faculty award committee, it gave me the opportunity to interact with a lot of people from other departments on campus in terms of the students. And it's like, oh, there are bright, exceptional students everywhere on campus. I just don't know about them because I never come into contact with them. So congratulations on making it to the finals. And I guess you'll find out tomorrow night, right? They are doing an awards thing. So yeah, that'll be good. Nice. Good job, I guess is what I'm trying to say. Not very effectively. So I'm a little discombobulated because I'm recovering from applied statistics. Which normally energizes me, but the computer going down in the middle of class threw me a little bit. So we had just finished talking about snake locomotion. And I was wondering if you had any questions about any of the locomotion stuff we've covered so far, or in particular, anything about snake locomotion that you might have questions about. Okay. As I mentioned before, the links that are in the PowerPoint are live, so you can go back and look at those again if you need to. So the 3 forms of locomotion that we had among snakes, can you guys see my screen? Okay, good. We're basically, standard what we think of as snake-like motion, which is called serpentine locomotion, and then we had sidewinding, and then we have rectilinear locomotion, which is where the animal anchors itself against the substrate with certain belly scoots, pushes the body forward. Once the front body has been pushed forward, anchors again, and then pulls the rest of the body up behind it. But it does this segmentally along the entire length of the organism, such that the organism just seems to be smoothly moving in a straight line, not really gripping on anything to the sides, but gripping on the substrate underneath the snake. And then we showed videos of those 3 kinds of rectilinear locomotion versus serpentine locomotion, so you could actually see the movements of the bodies And you can tell that the snake is doing these things because you can see the skin on the outside of the snake moving as the muscles underneath are manipulating the ribs of the snake. And then there's the issue of locomoting through water. So as Rose will tell you, there are snakes that live predominantly or around water, and they find themselves in water fairly often. Did any of you guys see the television miniseries Lonesome Dove or read the books Lonesome Dove? There is a scene where these cattle ranchers are moving cattle to Kansas City, actually, or to the north, but I think they were headed to Kansas City. Kansas City used to be a big rail depot, and people in Texas would drive their cattle northward to the railheads in Kansas City, and then they would get shipped. They would ship their cattle off to the east to go to slaughterhouses in St. Louis and cities in the east. And there was a scene where they were driving their cattle across the Red River, and they were set upon by a group of rattlesnakes that had presumably been washed out of the hibernaculum and into the river, and the snakes were swimming down the river, essentially trying to get to the bank when they ran into these ranch hands, some of whom got bitten and died by swimming rattlesnakes. Rattlesnakes are not typically found in water, and I don't know, that seemed like a very contrived scene in the book to me, but there are plenty of snakes that do occur predominantly or fairly often in water. The water snakes are one of the groups, so anybody in the genus Nerodia, you're as likely to find them in water as you are to find them on land. Thamnophis also are associated with water. Even some large snakes are associated with water. The anaconda, the green anaconda, is well known not only for being the largest snake in the world, but also being closely tied to water. And then there's a whole family of snakes, the Hydrophiidae, which if you think of them as their own family, they're in the Hydrophiidae, but they used to be placed in the family Elapidae, the poisonous sea snakes, live most of their life in the ocean. And in all of these cases, they basically adopt serpentine locomotion, but the serpentine locomotion, the object that they're pushing against is not fixed, it's water. So the water provides resistance, but it doesn't provide the same kind of resistance as fixed points would in standard serpentine locomotion. So when you're doing serpentine locomotion on land, there are fixed points that you push against, but depending on where those fixed points are located, it might put you into this kind of S-shaped serpentine body shape, or it might not. It all depends on where those hard points of resistance are. And so you see the snake locomoting through these pegs. That snake is undergoing serpentine locomotion, but it doesn't have a typical S-shaped pattern to the body because of the way that the hard contact points are located that the snake is navigating through. However, when you are doing serpentine locomotion in water, where the water is the source of resistance, and as you push against the water moves away from you, you get this undulation through the water that looks very much like what you think of as typical serpentine locomotion. So aquatic locomotion, which your book refers to as undulation, is simply serpentine locomotion in an aquatic environment where the resistance is there, the side-to-side resistance is there, but the side-to-side resistance isn't rigid. It's more flexible. And so this is a snake locomoting through the water. And if you've ever seen a snake swimming through the water, this should be fairly familiar to you. But the main difference is it's the same muscles being activated. The difference is really just the resistance to that pushing of the snake provided by the environment. Less resistance, more flexible resistance versus fixed resistance. Aquatic locomotion in frogs and toads is different though. There is, in this case, frogs, for the most part, and I'm trying to think of a frog that locomotes other than this in water, they basically do this kick and glide. And so they essentially use their hind limbs primarily for locomotion in water. They kick using their webbed feet to propel them forward. And after they've kicked once, they will glide for a period of time, and then they will kick again. And so it's just a series of kicks and glides, and they can come fairly quickly. So the kicks can come fairly quickly in succession, but if you were to film it and slow it down, you would see that there are short gliding periods between each kick. One of the nice things about that from the standpoint of catching frogs in the field is once a frog gets into the water, knowing that it does kick and glide, the only time that it can change direction is when it's kicking. So if you can get to the frog during its first kick and glide, you know that it's going to be moving in a straight line until it kicks again, at which point it might turn, but it can't turn during the gliding portion as easily. And then we have aquatic locomotion in the sea turtles. And the sea turtles locomote primarily using their forelimbs, which are modified into these big flipper-like structures. And when they are they're basically flying through the water, essentially. They're moving through a fluid environment. Air is a fluid environment. And they're basically using an oscillatory motion. And so you see, if you follow the tip of the leg here, you would see that it goes in a figure-8 pattern. So it goes up, moves to the front, pushes to the back, pulls up, and then goes back to the front, pushes to the back. And it's just this constant figure-8 motion. And it's this downward and pushing to the back stroke that basically powers the turtle forward. And what's interesting about this is that this is the same, although convergently evolved, of course, this is the same type of motion that you see in hummingbirds. And so when hummingbirds are hovering, you will also see that the tip of their wing takes on this figure-8 pattern. And so you have to have a slightly different joint in order to accomplish this type of locomotion. And that same structure of joint is found both in hummingbirds and in sea turtles. So once again, a convergently evolved solution to a similar problem, basically locomoting through a fluid environment. And whether the fluid is water or the fluid is air, the biomechanics are roughly the same. It's just one fluid is more viscous than the other. Plenty of animals burrow. And when we think about burrowing, we can think about burrowing in caecilians. We can think about different types of snakes burrowing, and then the amphisbaenids burrow. There was I think I've mentioned that I'm on a Facebook group called Field Herpetology. And on Field Herpetology, people basically post photos of herps that they have found in the field. It's interesting because there are people from all over the world on that site. And so you can see examples of herps that you will never come into contact with. But a couple of weeks ago, somebody posted a picture of an amphisbaenid from Baja California Sur, the Baja California Peninsula down in Mexico. But they live virtually their entire lives underground. And so they are burrowers. And in some cases, you can burrow using spades. So this is what the spadefoot toads do, both the Old World and New World spadefoot toads. You also have head first burrowing. And what you will usually see in species that burrow using their head, you will usually see reduced number of bones in the skull and more skull fusion. Go back and look at the figures of caecilians that we covered back when we were doing amphibian diversity, and you will see that that their skulls are much stronger than the other amphibian groups in terms of how compact their skull is in and how much bone fusion there is. And then other organisms combine head burrowing with concertina motion, which we'll see here in a minute. It's a little difficult to describe without a figure, so I'll just leave it until we get there. And here it is, right here. So in these species, so this is actually an amphisbaenid. It's a reptile. It's sister group to the squamates, and it lives primarily underground. And so this is the head end, this is the tail end. And what happens is the skin is loosely attached to the body, such that the skin, which would normally be anchoring the animal in its burrow, is loosely attached to the underlying tissues, such that inside of its skin, the animal can essentially coil up its body. So you'll see that it's called internal concertina motion. The animal basically pulls up its body, even its vertebral column is pulled up inside of its skin, and then uses that then as an anchoring way. As it pulls its internal body up into the skin, it makes the body thicker, and then it uses that thickness in the burrow to anchor itself against the sides of the burrow, and then that anchoring allows it to then push its head further into the soil, clearing out new space of the burrow. Once it's in that new space of the burrow, pulls its body up inside of its skin, pushes out against that burrow, the walls of that burrow to anchor itself, and then pushes the body forward again. So just a very unusual form of locomotion. And this is a X-ray of an animal in the process of doing this, and you can see that the outline of the Sicilian, or not Sicilian, the outline of the amphisbaenid is still smooth, but you can see the vertebral column inside the animal has become all curled up. Once again, just like the Sicilians, these things have very heavy skulls with a lot of bone fusion and modified into, in this case, shovel-shaped structures versus laterally compressed, such it's kind of like a vertical blade going into the soil. And so different types of skull morphology, but they're all skull morphologies that are adapted to different burrowing styles. This figure is not in your textbook, but this skull type right here essentially corresponds to this animal right here. And so these are organisms with shovel-shaped heads. And in this case, these guys are going to be locomoting through sand. And so one of the things that you find with sand-dwelling organisms is they tend to have very smooth, flat scales. So this, I believe, is a type of skink. This is a type of snake. Because sand is not a very well-constituted soil type, you can't build permanent burrows in sand. And so what you're basically doing with sand swimming is you're essentially doing serpentine locomotion through what is essentially a fluid environment. But in this case, the fluid environment isn't water or air, it's sand. It provides, once again, resistance as the animal pushes against the sand, but that resistance is somewhat flexible rather than fixed point resistance, like you would see in regular serpentine motion. And in this case, both of these animals have spade-like snouts that allow them to push through the sand effectively. Many skinks live in sandy regions, and the cycloid scales, you'll remember from seeing the skinks in lab, they had very sleek, smooth surfaces to their bodies. Cycloid scales are especially adept at moving through sand. And then, of course, we have climbing species. The chameleons are unique in the lizard world, this is a chameleon skeleton that has been basically attached to a stick here in the middle. And do you guys remember what the toe arrangement is of chameleons? They have a specialized toe arrangement.
Isn't it zygodactyl or something like that?
It is zygodactyl. Awesome, Rose. That's
Hell
pulling it
yeah.
out of the memory banks. What's that?
I said, hell yeah.
Yeah, no, that's good. So normally we think of your hand being like this, and for us we have an opposable thumb so that we can grip around things. But lizards don't have a thumb that is opposed, so they would grip around things, if they gripped around things at all, with all of their fingers for the most part, all their fingers and their thumb. But what happens with chameleons is they have a reduced number of digits actually, but two of these are turned around so that two of them face one direction and two of them face the other direction. And what that enables them to do is it enables them to reach around things and have very firm attachments to things like twigs, because chameleons are arboreal. And that zygodactyl toe arrangement is found not only in chameleons, which once again live on twigs and use that toe arrangement for grasping things, but it's also found in woodpeckers and nuthatches. And so if you ever look at a woodpecker or a nuthatch, as it is perched on a tree, two of the toes are sticking forward and two of the toes are sticking backwards. And that gives it a very firm attachment on the side of a tree that it wouldn't have if it had the typical 3 toes in the front and 1 toe directed backwards. And so once again, we see a convergent solution to a common problem. The other interesting thing about chameleons is their limbs are much more slung under the body than the limbs of a typical lizard would be. And once again, this has to do with just, once again, their method of locomotion, where they're generally traveling along the surface of thin twigs. So if you're climbing and grasping, one of the things that you might do is you might evolve specialized grasping structures that allow you to grasp onto the things that you need to. And that's the case with chameleons. Snakes are in many cases arboreal. Let's go to Facebook for a minute, because I wanted to show you guys this. Groups. Ignore the text emoji for shoot me in the head. I no longer want to be shot in the head. Field herpetology. You guys see the Facebook? Yeah, okay. So the cool thing about field herpetology is you see all kinds of cool animals from all over the world. But a few days ago, someone posted a photo. Now I wonder how many posts I've missed while I was working. Well, you guys know who that is. So here's a rat snake, and this rat snake is climbing up a tree. And so our black rat snake, Pantherophis obsoletus, here in the Midwest, occurs throughout the eastern United States and southeastern United States. I mentioned that some time ago that when I was a graduate student, my major professor would get calls from people who had snakes in their house, and he would send his graduate students out to deal with them. And the reason for this is that rat snakes are well known for climbing trees. They can go up vertical surfaces as long as they have some bark to grip onto. They're gripping onto the bark with their belly scales, and they're really adept at doing this. And when they get up into a tree, sometimes they leave the tree and fall onto people's roofs. And then once they're on the roof, they will crawl down the chimney, and then you end up with a rat snake in your living room. And these guys feed on flying squirrels in many cases, and so they'll go up to flying squirrel nests. They will also feed on woodpecker nests in holes in trees, And so their arboreal lifestyle is pretty well documented. But while they're doing this, you may need to get from one tree to the next tree. And so there's this technique that they use called gap bridging, where they basically anchor themselves at one end. And you can see that this is a pipe that the researcher has just put dowels into, and he can space the dowels out as to whether they're closely spaced or further away spaced. And then it has given the animal a gap to bridge. And what you will see is that the animal can basically extend the anterior part of the body over the gap until they have a firm attachment point at the other end. And then we'll start the process of once again pushing against these fixed resistance points to use serpentine motion to then pull it further onto this limb as the rest of the body comes up on the other end. If you extend the gap that is being bridged, though, that's more of a challenge. And you can see that the arrangement of the snake's body has changed. Before, the snake was perfectly happy to just leave its body between the little V-shaped groove that is formed by these dowels. But when a snake is faced by a longer gap to bridge, one of the things that you will see is that the snake begins to anchor itself more firmly at the anchoring end. That anchoring then allows it to extend more of its body out over the gap. And you'll also see that as it has its body anchored under this dowel, that provides leverage so that it can raise the upper part of the body. And the higher the upper part of the body is, the further out you can reach in order to make contact with this. So snakes will adapt, within any climbing and gap bridging situation to what the needs are to get across whatever gap they're trying to bridge. This is referred to as lunging, where they're basically anchoring themselves. They build themselves up, and then at the end they kind of lunge for the contact point. And then at that point, once you've got a firm contact point, you can start serpentine motion and pull the rest of your body across that gap. And then adhesion is another thing that is useful for climbing. Adhesion happens in a number of different groups among the frogs, and these are scanning electron micrographs of frog toes. What you will see is that the frogs have mucus pores, and they exude mucus out onto the toe pad. That moistens the toe pad, and the toe pad basically acts kind of like a suction cup onto whatever surface that they are trying to adhere to. You will notice that, well, remember, what is one of the distinguishing characteristics of tree frogs relative to other families that has to do with their toe structure? A frog's toes have phalanges just like your fingers have phalanges, but the terminal phalange then makes contact with the toe pad. But what's between the terminal phalange and the toe pad? It's a distinguishing characteristic of the family Hylidae. Anybody remember?
The cartilage, the intercalary.
Yeah, in the intercalary cartilage, yep. So there is a cartilage that is not found in other frogs that basically bridges the gap between the last phalange and the toe pad. And that thing, because it's cartilage, it's more flexible. And as that thing flexes around, it allows the toe pad to, regardless of what the orientation of the rest of the toe is, it allows that toe pad to sit flush against the surface, which then enables the animal to adhere to whatever it's trying to adhere to. And so in some cases, you might see a tree frog where the surface that the tree frog is adhering to is here. The toe pad is sucked right down onto that. The intercalary cartilage is here, and the whole rest of the leg is, the whole rest of the toe is actually flat on the surface. And it's that intercalary cartilage that enables the toe pad to bend around and be flush on the surface. And it needs to be flush on the surface because it basically is using that toe pad to adhere to the surface firmly, just as a suction cup does. What facilitates that also is just like if you're attaching your GPS to your windshield, if you apply a little bit of water to that before you attach it, it's going to make a much more firm attachment than if you didn't do that. And so the purpose of these mucus glands is to lubricate that structure so that it makes a nice tight suction to the surface. That's very different though than adhesion in lizards. So in geckos are well known for having these toe lamellae. Let me write that term on the board. These toe lamellae are found in geckos, but they're also found in anoles, although the structure is slightly different. They're similar in many ways. And so when you look at the underside of the toe of a gecko, you'll see these rows of toe lamellae. When you begin to blow those toe lamellae up, you see that they do make actual little rows. But then when you start to look at the tips of these toe lamellae, you see that each of these things is divided up into little subdivisions, little almost like squares that are then subdivided even more. And when you start to zoom in on the actual little squares, you see that they look like this. And when you zoom in even more, you see that they're made up of all of these little spatula-shaped objects, spatula-shaped tips. So these are the individual tips. You can see them, individual tips here, 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 and here. And then those are all bundled into these. I always think of them as looking kind of like broccoli stalks that then come off of the main structure of the scale. Well, it turns out that these things are so numerous that when they come, or they're so tiny rather, that when they come into contact with other surfaces, they actually adhere to the surfaces that they are on with van der Waals forces. Do you guys remember what van der Waals forces are? From basic chemistry?
They're pretty weak interactions, but aren't they like the positive and negative, like brief
Yep.
periods that they attract and then or repulse each other?
Yeah, they're one of the weak intermolecular forces. Once again, they're based on charge, and you can see that this is a micrograph of the tip of the lamella adhering to the surface that it is attached to, and you can still see the outline of the lamella. But when the van der Waals forces are activated, they basically flatten that spatula down so that it's firmly adhered to whatever surface it is on. Because they're weak intermolecular forces, they can be formed and broken fairly easily. And they're normally so weak that they wouldn't be very useful for doing something like holding a gecko on a wall. But because you have millions and millions and millions of these lamella tips interacting with the surface at any given moment, the collective force of them is enough to keep the animal firmly attached to whatever substrate it is attached to. So it's one of those situations where each individual attachment place is very weak, but the combined force of all of them, because imagine here's each of these. Each of these is on an individual stalk. There are hundreds of individual stalks on each of these clusters. There are thousands of these clusters within a given lamella, and there are hundreds of these lamella on the bottom of a toe. You add up all those collective weak van der Waals forces, and you can get quite firm attachment of a lizard to a pane of glass. And so when you see geckos out in the field, you will see them crawling over rocks and brick surfaces, but you'll also see them run onto glass, and they can run across glass just as adeptly as they can run across a brick surface. The one place where I see geckos not doing particularly well is on metal. And one of the things about metal is that in many cases, the metals that they run across have an oxidized surface on them, and that disrupts these molecular attachments that they have, these weak intermolecular attachments that they have. And so I'll oftentimes be chasing a gecko up a brick wall. It gets to a piece of metal flashing, and as soon as it does that, it can't grip anymore and it'll fall off the wall. But it can attach to glass quite well. If you've ever felt glass and paid attention to the feel of glass, glass definitely has a really strong electromagnetic charge to it. A lot of times if you get your arms of your hair up against glass, you'll see that your hairs on your arms stand up a little bit near glass, and it's because they're reacting to the charge that glass has. And so they're particularly good at gripping onto glass, whereas other organisms cannot. This is interesting because there is a guy at the University of Massachusetts Amherst who works on anoles, actually, and he has begun collaborating with some people in the material sciences department at the University of Massachusetts, and they have started developing applications of this type of adhesion to make a thing called geck skin. So I'm going to try this. And I have generally failed at getting you to hear audio, but I'm actually going to try it again. Can you guys hear that? No, okay. All right, pause. Give me a minute to see what I can do about let me try something here. Okay. Can you hear it now? No. All right. This actually is one of those situations where having them explain it would probably be better for you than having me providing voiceover. So let me see if I can figure out a technological fix for this. Okay. Give me a minute. I'm going to reshare.
If you take out your headphones and play like the audio through your computer speaker, we might be able to pick it up if it's unmuted. I have no idea if
Okay.
that'll work.
Okay. I have my headphones off now in terms of acting as audio. But let's see. Checkbox in the lower left. I don't see a checkbox in the lower left. Okay. All right. Let me do all of this. Okay. I'm going to turn up my volume really loud.
I'm Al Crosby.
I'm Duncan Ershik.
And we're the
Can you hear that? Okay.
Skin team.
The GECSkin team of Crosby, Ershik, Andrew Kroll, and doctoral students Mike Bartlett and Dan King here at the University of Massachusetts Amherst a new adhesive device made of simple, inexpensive materials that can hold up to 700 pounds on a smooth surface. It's based on some key anatomical properties of the gecko foot, which is covered with millions of little hairs called setae. Crosby and his group hypothesized that the setae alone are not the only feature allowing a gecko to adhere to walls. They suggested that a stiff tendon directly integrated into the skin is also critical.
So these are the properties that we've been trying to work on, are really high capacity, easy release.
And these geckos have done that by making millions of little hairs, which are so small that they can get very close contact with the surface, and that provides force they need to climb. But our contribution that Al and I have really worked on, along with Mike Bartlett and Dan King and other people, is to really look at actually the whole organism, to look at not just the hairs, but also to look at the underlying anatomy, look at the tendons and the soft tissue, the skin that underlie this foot structure, because it really is a...
Notice that this picture that you're seeing right here has the toe curled up. And actually, this is how they walk. This is not them putting their toes down. This is how they lift their foot off of a substrate when they're beginning to pick up their foot and move it to someplace else. They actually start lifting their foot, not from the palm up, but actually from the tip of the toes up. And by removing it, by removing their toes from the tips up, it allows them to separate each of these individual strips of CT, each lamella itself individually, once again, reducing the total force that's holding the tip of the toe on there. Easier to take them off one lamella at a time rather than trying to pull it off all at once. And so you'll see this as a very typical way in which geckos lift their foot rather than the way they put their foot down.
whole foot. It's not just the hairs.
The key innovation by the GECSkin team was to create an integrated adhesive with a soft pad woven into a stiff fabric. This allows the pad to drape over a surface to maximize contact. Further, as in natural gecko feet, the fabric is woven into a synthetic tendon, yielding a design that maintains stiffness and rotational freedom using everyday materials.
And what it does is it just drapes easily over the surface, gets close enough that the van der Waals interactions can become strong, and it can hold, 700 pounds, maybe on an index card size pad. But then with a simple, twist of the pad, it peels off with zero force, and it doesn't mark the surface at all. And one of the really important things is that you can do this over and over and over again.
What's unique about GECSkin is the kind of use of very simple materials in a very novel way.
GECSkin opens up new opportunities for adhesion that we've never envisioned before.
We are on the verge of a giant leap forward in technology. It will take mankind to new, unscaled.
Stop. Okay,
In the name of
My computer is rebelling against me. You guys hear me? Can you guys hear me now?
Yes.
Yes, okay, thank you. Okay, so what are your thoughts about that whole thing? You guys can hear it okay?
Yeah.
Okay. So one of the cool things about that is it's just a nice application of herpetological knowledge. The other kind of cool thing about it is, you know, we have these 3M hooks and things like this that have an adhesive on it that supposedly when you put it on something, you can take it off easily. And that works usually, but I've used them plenty of times and it's taken off a little bit of paint after when you go to remove those little temporary hooks. One of the things that's cool about this is the fact that you can attach this to something. It's amazingly strong, and yet when you pull it off, it doesn't do anything to the surface. And then it's also perfectly reusable. From a material science standpoint, it's kind of cool in that way. From a marketing standpoint, you have to think that if they ever bring this to market, people will buy it once and then never have to buy it again because it's just usable over and over and over again in the same way that a gecko toe pad is. Anyway, just one of the interesting applications of there's this general field in engineering called biomimicry, and it's essentially when engineers look to solutions that have evolved in organisms and then adapting those solutions to problems that that human beings are having. So gec skin is one example of this. They're interested in using this in applications for like attaching things to other things, but they are also interested in this in adapting it for like the use of special forces. If a special forces person needs to scale a wall, well, you could do that with ropes and climbing gear and things like this, but you could also do that in theory with you know, gloves made out of gec skin or something like that. Another application of biomimicry, what's known as biomimicry, is the butterfly wing has scales on it. And for a long time, people thought that the main purpose of scales was to provide color to the wing, but a group of material scientists working with biologists were looking at the thermoregulatory properties of these scales on butterfly wings and found that they're also very useful at dissipating heat. So imagine that you're a butterfly out there in nature, you have the sun beating down on you. The surface of your wings are basically like big solar collectors. They're exposing you to a lot of solar energy and they're causing your body to heat up very quickly. And so one of the functions of the scales on butterfly wings are they have these little scales that allow heat to be dissipated off of the surface of those. And what computer chip engineers have done is they've engineered scales, similar scales in structure to butterfly scales onto computer chips, once again, to dissipate heat. Because one of the things that happens with the computer chip is as it's processing information, it warms up and you have to dissipate the heat in order to keep it functioning. If a computer chip gets too hot, it begins to affect the performance of that computer chip. So there are lots of adaptations that organisms have evolved that then have practical application to humans for a variety of different challenges that humans may face. Gec skin is one of them. Scales on computer chips is another. And then aerial locomotion, I think, is the last section of this chapter. Aerial locomotion can include falling, which seems weird to include that, parachuting and gliding. And the difference between these things is falling is not particularly controlled. Parachuting and gliding are controlled, and parachuting and gliding are separated in terms of the not only the aerodynamics of it, but also the directionality of it. Parachuting is more vertical. You're just basically using aspects of your morphology to slow down your rate of descent, whereas gliding, you're using your body to basically not only slow down your rate of descent, but also direct your descent to a particular place. And so there are a variety of different ways in which organisms accomplish this. If you're in a free fall, there is some resistance as you spread out your arms and legs. You can provide resistance, and that will slow you down, but it won't slow you down as much as if you have special modifications like very large pads between the very large webbing between the toes, where each hand kind of acts as a little parachute, which essentially reduces your rate of fall, and can also result in directionality of your fall to a certain degree. This is a type of tree frog that is known for parachuting. These are members of the genus Draco, which is a group of lizards that live in Southeast Asia.
Slides right now.
What's that?
You're supposed to be looking at the slides.
Oh yeah, I did not make a good transition between video and here. Yes, can you see it now?
Yeah.
Yeah. Okay. So yeah. So here you have a frog with large webs between its toes. This allows more air surface to be caught, and it does two things. It essentially increases resistance, which reduces the speed of descent, but you can also use this to change direction to a certain degree, as opposed to a frog that is in free fall, where there is resistance caused by the legs, but there's very little ability to apply any sort of directionality to it, and the increase in resistance isn't nearly as high as the increase in resistance when you have large toe webbing. In members of the genus Draco, which is a group of lizards that lives in Indonesia, you basically have a flap of skin that can be extended by the ribs. You can see that the ribs are outlined in light gray here. And this essentially forms a gliding wing that catches air and acts as an airfoil and causes a lot of resistance, but also causes quite a lot of lift. And these animals can actually glide pretty far distances as they move from one tree to another tree. And so different degrees of resistance lead to different degrees of directionality. Essentially, the more resistance you have to fall, the more directionality you can exert over this. And these animals will basically jump off of one tree, glide to another tree, land on the surface of the trunk of that tree, and then scurry up it. And they're really quite good at that. It's not only things with legs that can glide, but there are also snakes that are capable of gliding. And what they essentially do is they flatten their body, and so they'll coil themselves up on a branch. They will basically lunge out into space, let go of the branch with their tail, and then as they begin to fall, they flatten their body. And when they flatten their body, it basically forms a wing-like shape, and you'll basically see the snake essentially slithering through the air or undulating through the air. And so once again, we get back to this idea of locomotion within a fluid. It doesn't matter whether that fluid is air or whether that fluid is water. The biomechanics of it are pretty much the same. So this is one of the gliding snakes. You can see it sitting on a limb here, but then this is it in flight, and you can see that its body is much flattened relative to when it's not in flight. And once again, I have video of this going.
So I will attempt to show this again and see if so this is actually a New York Times thing. So I'm gonna pause recording on Zoom so that I don't get dinged by YouTube for violating copyright. Purposefully jumping off of the stick, and then you can also see the trajectory of them. They're not just plummeting to the ground; they're actually directional in terms of they're basically leaving the stick here and they're landing on the ground somewhere over here. And so that's kind of the very definition of gliding in this case. And this is actually the snake image that you saw in that video, because this came from the publication that it was, or maybe this is actually from your book, from your textbook, but it's from the publication that was originally the publication of the research. The other thing that I find interesting about that video is, of course, the undergraduate students or graduate students who were basically hired to hang around underneath these snakes coming out of the sky so that they could grab the snakes before the snakes slithered off and escaped. Once again, this is done by a group of snakes that are found primarily in Southeast Asia. And I'm not sure what it is about the environments of Southeast Asia that make gliding so commonplace there, but all of the examples in your book, if I recall correctly, of gliding and parachuting animals come from Southeast Asia. And I think that finishes the chapter on locomotion. Any questions? All right, today was Friday, so tomorrow is Friday also, but Friday is Undergraduate Colloquium Day. If you have friends who are presenting, come out and support them, and enjoy your weekend, and I will see you guys on Monday.